So let's start, and let's start with the name Diana. Diana is a short form of displacement analyzer, and is a general finite element program which is dedicated to all types of civil engineering structure, including bridges and infrastructures, geotechnical as well, and petroleum engineering application. Our aim is to provide a range of efficient engineering solutions to the daily or specific types of engineering problems that by increasing the accuracy of the final results, our clients could optimize the cost of their project. On this slide are displayed the core value of our companies based on the trusted relation with our clients and partners. We try to mature dynamic and innovative ideas to deliver state-of-the-art solution and quality service in a world-class product. On the next slide, we present a list of some of our valuable clients. We have clients in different countries all over the world from different organization type, from a governmental organization, academic, university or research organization, but also from private sectors like consultancy companies or construction companies, from different sectors, oil and gas, energy, and infrastructure. We appreciate their effort in trusting and using Diana in their daily project and activities. With respect to Diana application, I quickly go through some of the main key features and activities. We start with geotechnical and tunneling. We have a very good integrated solutions for all type of geotechnical and tunneling applications. So you can use integrated environment of Diana for any types of tunneling and underground structures. For ground freezing, also called the three-phase analysis. For real soil structure interaction, so if you have some sort of interaction between the underground and the surrounding soil or rock, you can model it with the concept of nonlinear interface behavior. Coupled groundwater flow stress, also for excavation and temporary structures, pyrite foundation, earthquake, blast and vibration analysis, drain or undrained soil behavior, large deformation and strain, embankment on soft soil consolidation, slope stability, and many more. And as you can see here on this on the bottom right corner, we have also many wizards in Diana for modeling of piles, sheet piles, including predefined library of parameters. You can see here with some section, predefined section from a sheet pile wall wizard. Next to that, we have a very comprehensive solution associated to reinforced concrete and early age behavior of the concrete cracking. That's mainly when the model and the casted concrete goes through the process of hydration. For any types of concrete box girders, composite structures could be interaction of concrete with metal or combination of concrete with fibers. For dam structure, it's also very important because of the process of casting, clearing, hydratation, and impounding. We also have a good coverage for design check, including reinforcements based on the Eurocode, mobile load and design load generator, and indeed the cross-section design check. You can use it in conjunction with your bridge applications or your general structural analysis application. We have different solutions in order to give you a good estimation about nonlinear response of the model without entering into the nonlinear detailed parameters input and setup iteration like sequential linear analysis. Temperature and stress coupling let your analysis let you analyze how the concrete goes through aging. Cooling pipe is also another powerful feature that we offer in the both context of 2D and 3D in order to control the hydration process. Crack initiation and the propagation in the concrete structure is one of the powerful feature in Diana. And also fire effect, how the fire could affect the durability of the structure. Among other applications, we can refer to masonry and historical constructions. In Diana, we offer different solutions at meso or macro levels. You can use Diana to model the interaction between the individual bricks and the mortar joints, for instance. For dams and dikes, Diana offers the solution. It covers all the aspects of construction for all types of dam structure. You can consider the fluid structure interaction, dynamic effect, and also induced damage to the structure. Fire analysis is another area that, based on its importance these days, has become one of the main topics for structural check. Diana can be considered as one of the most reliable solutions for that. For earthquake analysis, you can use Diana for general dynamics or seismic, such as frequency response analysis, transient analysis for both linear and nonlinear, hybrid frequency time domain analysis, and fluid structure interaction or liquefaction. Among the advanced type of application, Diana is very well known in the field of oil and gas and nuclear structures. Based on the type of complexity, you can simulate 3D geomechanical depletion, borehole stability, casing integrity analysis, mechanics of completed well. For nuclear structure, you can analyze concrete containments or underground race storage, and also assess their seismic performance, for instance. So we have a very complete solution for a large variety of application. Let's now look at the Diana environment. So this is our Diana interactive environment, also known as Diana IE. And I'm going to say a few words about the different window that we have. So like any Windows program, you have a toolbar at the top with different icons. These icons can be seen as the shortcuts to the functionality that are listed below the top menu items. On the left side, you can see that we have a model window with full access to the model components for both the geometry and the mesh. Below, you have a property window that gives you some in-depth information about some of the shapes or mesh or materials that you have defined and that appear on your model window. On the right side, you have the analysis window. That's where you basically set up your analysis and the type of options and results that you want to have. Below, you have the output window. So here is displays the output of your analysis. And that's with this window, you can basically look at your results and scan the different results. The main window here is the working window. That's where basically you developed or create your model, assign your properties, mesh your model, and look at your results. Below, you see that we have two windows. One is a message window. Over there, you can monitor your activity, and if something is wrong, that's where the error message are displayed. But you can also monitor your nonlinear analysis in terms of convergence. And next to that, one of the strong features is that we have a command console, which will echo the Python command. Diana has a Python interface, so every actions that you are doing in terms of clicking result in a Python command. And this Python command can be echoed in the command console, but as well as in a text file, which is automatically saved on your system. So it's a very powerful feature because it allows you to replay your model at any stage using the Python script capability. In terms of graphical tools, Diana IE offers an intuitive user interface with various display options and advanced selection methods. Modeling functions are based on Parasolid, and it has also automated and robust geometry checking and repairing tools, which is also very good when you deal with CAD model. In terms of machine tools, we offer powerful and automated mesh engine, both 2D and 3D, including hybrid mesher. You can generate embedded reinforcement, and Diana has an automatic element type selection. For loads and boundary condition, Diana IE offers full support of loads and boundary condition. And everything is defined at the geometry level with some flexibility to assign some of these loads and boundary at the mesh level. But generally speaking, everything is done at the geometry level. You can define function, and you have full compatibility with in terms of tables with Microsoft Excel, so you can easily copy paste your data from one or the other way. In terms of post-processing, we offer a complete solution to result interpretation. From material models classification, we have separate dialog boxes with various input fields for every material model. Unique aspects can also be activated in the material models. As you can see here, I mean, the aspects to include, you can just check on, check off. Interactive tables for function and variable dependency are also available. In terms of load combination, you can generate distinctive load combination for analysis via the load combination table, but you can also generate design load combination as well. In terms of function, you can generate various functions, such as a spatial or non-spatial function or a space function. I will put that in application in our live demo of today. The property window gives you full control on parameterizing the selected operation. The analysis window is intuitive and gives you an easy access to the setup of your analysis, including phased analysis. So you can, in a few clicks, just select and activate the phase that you want to be active in your construction stage of phased analysis. And many more options are available. In terms of workflow, we start with the geometry definition, always the geometry definition in Diana IE. Then you assign your properties in terms of material, boundary condition, and loads. You generate your mesh, so you assign your mesh settings and generate your mesh. You set up your analysis. So you define whether if it's linear analysis, structural non-linear analysis, and the different options. You run the analysis, and then you check the results. And everything is done in the same environment. The thing that you have to be aware is that any change in physical property, material property, or boundary condition done at the mesh, at the geometry level, require you to rerun your analysis every time. But this is the general workflow that we use in Diana. In terms of geometry modeling, we have many options to create the geometry of your model, as you can see on this slide. You can either import your geometry from third-party CAD program or generate your model from your integrated environment. Among the formats that Diana IE can handle are DWG, DXF, STEP, and IGS. You can also import IXC file format if you are using Revit. Furthermore, if you are dealing with terrain geometry, for instance, you can import cloud of nodes and generate Bezier surface from this cloud of nodes. After importing the geometry, there is a geometry check. You can always check the tolerance and the quality of the imported shapes. You can fix it, improve it based on certain features that we have in Diana to enhance your imported geometry. Otherwise, you can use basic tools we offer in terms of modeling primitive to create and generate your model for 3D, whether it's a block, cylinder, prism, torus. And you can access more information about the type of geometry entity from the shapes by selecting them from the property window. You will see the entire entity as attached to your shape. And also for other 2D and 1D geometrical entities, we have some primitive as well. And again, once you create this primitive, they appear under your shape in your model tree, and you can access their sub-entities in the property window. You can perform different modeling operations, such as unite, subtract, or intersect, or transformation, such as move, scale, or rotate. You can sweep your geometry. Here in this example, we have a reference shape, for instance, that we sweep along a wire, which is a beaded curve, and it can be curved. And you can, in a few clicks, generate the solid of such a bridge tape, for instance. You can generate a complex geometry with minimum information using some smart function available in Diana AI, like lofting operation. Here are some of the examples. Our selection window is fully interactive and object-oriented. You can directly select them based on the selection filter. So you can see that the selection filter offers quite a range of options, and based on your choice, you will be able to select a specific entity. So if your selector is set to shapes, you will be able to select shapes. But for instance, if your your selection is based on edges, you will only be able to select edges type entity. For modeling, we are using auto clash detection, so you don't have to worry about nodal connectivities of the different components of your geometry interacting with each other. Diana automatically take care of that for you, ensuring perfect continuity and connectivity for your mesh. There are other options in order to improve your geometry, such as CO2 or more sheets, or convert body and sheet. So these are very nice and powerful features. For any operation in the model with respect to the loads and boundary condition, you can use imprint options to have the trace and track of the imposed loads or boundary condition acting on your reference geometry. Other modeling operation enables you to rotate or move, phase, or adjust your shape. So you can do that via dialog box, but also interactively in the working window. You can select and extract subshape and extrude this selected face and edge at any stage in your geometry. You can match different parts of your model with respect to each other using the aligned face function when you have different objects in your working environment and using the different alignment options that are offered. With respect to the function, it can be assigned to the geometry to simulate the geometry thickness, for instance, like in this particular case where we have the thickness as a function. Or you can define it or you can define your phreatic water level in both 2D and 3D modeling environment. This is a powerful feature in the context of geotechnical application, for instance. Another strong feature in Diana is Python scripting, as I mentioned earlier, and the geometry optimization with respect to the effectiveness of the model when it's subjected to such a vertical load. And now you can reinforce and retrofit the model because of the load distribution pattern in the model. There are many powerful features that you can induce and use in conjunction with other tools that we have in Diana based on the Python scripting. Another strong feature in Diana is the meshing capability. We have different type of mesher. These are smart process. They recognize the generation of your geometry. If your geometry is based on extrusion, extrusion mesher come into the picture and generate a nicely pattern and structure mesh, as you can see on this picture here. We have adaptive element size option that enables you to increase the density of the nodes and elements at certain corner and edges in order to have a smooth transition mesh. So you can see the difference with and without this option activated. Here also you can see this effect. If you have a terrain geometry, for instance, you can see the difference with or without the adaptive element size option. You can observe that with this option, you have a smooth mesh on some area where it's particularly curved. You can also use grading to optimize your mesh. You have full control on the distribution of the nodes and elements on the edges or in the face. After meshing, you can visualize the type of selection that you have assigned to the model based on the different profiles that we have in our library. This is done using the real dimension, and it enables you to check the orientation and eccentricity, for instance. And here are the different type of profile that can be visualized with a 3D cross-section based on the dimension that you have entered or the predefined one. At the mesh level, you have different way of presenting, such as wireframe, feature edge, shrunken view, that enables you to inspect or present your model in the most suitable way. Also, there are different mesh engine, which enables to generate structure or unstructured type of mesh set. Here are some examples of map mesh and auto mesh. So this model can be very elaborated. Another powerful feature is incremental machine. This is very interesting when you are dealing with a complex model and you need to do some modification at the geometry level for any reason. Thanks to this incremental meshing, you don't need to remesh the whole model. Diana automatically goes for the meshing of the geometry parts of your model that have been subjected to modification. This way you can save a lot of time in terms of meshing and the remeshing of your model when subjected to change. And for instance, in this particular example, you can see that the time of meshing and the time of remeshing can be divided by a factor 6, just thanks to this technique of incremental machine. So it's kind of very powerful. And at the end, we have a series of online documentation, including verification report with and benchmark report as well as our backbone theory. So we have a very comprehensive set of documentation, which is available online, but also available on your installation when you install Diana.
Good afternoon. So I'm doing today a live demo of a pushover analysis of a Masonry house. I will go through the main steps of doing such an analysis. And to start, I want to first give a short overview on this type of analysis. So there are mainly two options to perform a seismic analysis, and one is a nonlinear model pushover analysis that we are going to see today, and the other one is the more complex nonlinear time history analysis. So to start with, the pushover analysis is a static nonlinear analysis in which damping and cyclic behavior are not considered, and a lateral force equivalent to the model distribution is applied to the structure. So there's a generalized form of the load that is dependent on the mode shape, and this would be very complex and time consuming to do this by hand, but at Diana we have this pushover force, so this lateral force that is equivalent to a given modal distribution. This is computed automatically in Diana. And these analyses, they are quite simple and they are fast, and that's why pushover analysis is a well-established procedure and is considered in guidelines and codes to predict the structural capacity under seismic loading. Some drawbacks of this procedure is that only one mode shape can be studied at a time. So for complex and non-symmetric low structures, the dominant mode might not be clear, and you might need to study different mode shapes in different directions. Another point is that the dominant mode can change due to damage, and that is not accounted in a nonlinear model pushover. On the other hand, we have the more complex solution, which is the nonlinear time history analysis, which is complete transient dynamic analysis in which damping and the cyclic behavior of materials is accounted for. And we also have the ground motion in terms of the acceleration history with time in the three directions. So this analysis actually solves the equation of motion. And of course, this is a quite accurate structural assessment. It accounts for the correlation between different modes, and it gives us a realistic output of the development of the structural response in time. So in terms of damage, displacement, cracks. Well, the cost of this is that it is quite complex, so it comes with a computational demand, and because of these, while the number of signals that can be studied in an analysis in a structure are quite limited. So today we are going to focus on the nonlinear model pushover analysis. And for this, we are going to simulate a small house which has masonry walls and has a roof made of timber and also timber beams for the roof. And it's in a ground foundation, so we don't model the ground itself, but we simulate the behavior of the ground by means of an interface with friction properties. So for the material properties, we will define the isotropic elastic properties for the concrete and for the timber of the roof. We will have elastic orthotropic for the timber of the roof plate, and we will have the soil interface with cohesion and friction angle and the lattice properties. And for the bricks, so for the masonry walls, we will use a material model Indiana that is called engineering masonry model. That is based on the smear crack approach, and it accounts for the head joint failure mechanism. So I'm going to start a new project. I will call it masonry house. So it's a three-dimensional model. The model size is 100 meters. We will keep the units as SI, and I will start the geometry with making the lines of the bottom of the walls, and then extrude them to make the wall. So I create the first line that is called wall 1x, and I put the coordinates. And create. So I will jump to the next phase of the model, in which I already have all the bottom lines of the walls created. So you can see it here. And I'm going to extrude these walls 3 meters in the zeta direction, so I can make the wall. So extrude, and I select the walls. I can select it from here. So 3 meters in the zeta direction. Apply and close. So now I'm going to make the door gap. So for this I want to make a polygon sheet. So I make a polygon sheet, and I take my coordinates from Excel. So I want to coordinate, and I click it. So you can see the door, create, close. So I'm now going to subtract this sheet of the door to make the door gap. So subtract. So the target is the wall, and the tool is this door, and I can preview, so I see the gap and apply. So now I'm going to create the lines for the beams of the roof. So I start with the first one, and I type the coordinates. You can see it on the screen, and create. And now what I'm going to do is to array copy this line 8 times. So we make the nine beams of the roof. So I select this beam, and I want to have a distance of 0.6 meters in the y direction, and I want to have 8 copies of it. So you can see it, apply, and close. The next thing I'm going to do is the sheet for the roof, and this sheet has 5 centimeters gap from the walls. So I'm going to make a polygon sheet and take the coordinates from Excel. So you see, and we can create. So I'm going to jump to another phase of the model, in which I already have the sheets that I need to create the ring foundation. So here you have. So I have these two polygon sheets, one for the outer boundary and one from the inside boundary. So I want to subtract one from the other to make the foundation ring. So that's what I'm going to do, to subtract the foundation from the foundation out. And I can preview and I see that I have the ring and I apply. So now I'm going to start the property assignment of the model, because the geometry is complete. So I have here all the materials that I need that are already defined. So I have the clay brick. So we use the engineering Masonry model. So I have the elasticity parameters, the cracking parameters, the crashing and the shear failure parameters, crack bandwidth, and I don't need the damping because this is a model pushover analysis. Continue with the linear isotropic model for concrete. So I have only linear material properties. I have the friction that is for the interface. So we have linear material properties and the Coulomb friction. And for the roof plate, I have elastic orthotropic material model, and that will be used with a curved shell element. And for the timber of the beams, I also use elastic isotropic material model. I also have here defined the element geometries that I need for the different shapes of the model. So we can start with the foundation. So we have defined the thickness of 0.5 meters. For the roof plate, we also have the thickness defined. Then we have for the interface, we have defined the local axis. For the timber beam, we have the cross section, the rectangular cross section defined. And then we need to define the thickness and the element axis for the walls in X and for the walls in Y direction. And the reason for this is that the engineering Masonry model needs to know where is the location or the orientation of the bed joints of of the bricks, and this will differ when you have the walls in the X direction or in the Y direction. So with this, we can start doing the actual property assignment. So we can start with the walls in the X direction. So I go to shape property assignment, and I select the two walls in X direction. And we are going to use regular curved shells, and the material model is the clay bricks, and geometry is walls X thickness, so we can apply. And now we continue with the walls in the Y direction. So the walls in the Y direction also use regular curved shells, the same material model, clay bricks, and the geometry is now walls in Y thickness. Can apply. The next one is the beams of the roof. So I'm going to select the 9 beams of the roof, and here we are going to use class 2 beams 3D, and the material model is timber, and the geometry is timber beam that we already defined. So we apply. And the next is the roof plate. I can select it here from the geometry, and I use regular curved shells, and the material is the roof plate, and the geometry is the roof plate also. Here, apply. So finally, we need to define the interface, and Sorry, we forgot to define the foundation. So the properties of the foundation, that is the concrete foundation. So we select the foundation, and it's also regular curved shells, and is the material is the concrete linear, and we have the foundation. Okay, so now we have the complete shape property assignment, and what we need now is to define our boundary interface, because at Diana we can, in the same widget of the connections, we can define an interface and also the supports. So in this case we will have the friction of the interface of that means, well, with the ground contribution, and we will also restrict the translations in the bottom of the foundation sheet. So we open the connection property assignment and we choose for boundary interface. It's a face, so we select the bottom face of our foundation, and the element class is the structural plane interfaces, the material is the friction, and the geometry is the surface interface. And now we can define already the support. So the supports, we need a new support set, and it's a face, and here we want to fix the translations in the 3 directions. So we can create this support, and now we can use it directly in our boundary interface. So if we create, we see that we have the interface and the supports. So now we want to define the loads. We start with the self-weight, so we want to attach a global load. So we are going to call it self-weight, and we add a new load case, and it's of dead weight. Apply. So when we create, we can see here in our loads browser, we can see our self-weight being defined. So now we are going to define the actual pushover load. So this lateral force that is equivalent to the dominant mode for the pushover, which is the sway mode. So this is a lateral force equivalent to that modal distribution, and that is automatically computed in Diana. So that would be something that would be very difficult to do manually or lots of work, and that's what is automatically computed. So we go to loads, and we define our pushover load, and the load case can also call it pushover. And here in the load target type, we choose for shape, and in the load type, we select the model pushover. In the loaded body, we select all the shapes of our model, because we are going to consider all the shapes in our pushover. For the loading direction, we define all directions. In the acceleration, we need to provide the acceleration of gravity. And here is the eigen mode to be considered. So this is the sway mode, the lateral mode, the mode that is dominant for the pushover. And this is something that we will need to confirm after an eigenvalue analysis. But to start with, we will consider that the critical eigen mode is number 1, and that we will confirm in the eigenvalue analysis. So we can create the load, and we can see here in our geometry browsers in the loads that we have our pushover load defined. So now the only thing that is missing is to define the mesh. So first, the mesh properties, to clean the mesh, because I clicked clear mesh, see geometry, generate mesh without mesh properties. So first I'm going to define the mesh properties. So I want the element size, and I want to select the roof plate and all the beams. and the roof plate. And I defined 0.6 element size. So I apply. And now I want to select the remaining shapes and give a desired element size of 0.3 meters. So I apply. And now I can generate a mesh. And now I have a nice mesh. So the next thing I'm going to do is an eigenvalue analysis. So let's go to that step. Here I have defined an analysis for a structural eigenvalue, and I want to execute 5. So I want the number of eigenfrequencies I select is 5. So I click run, and we can wait a little bit because this runs fast. We can see in the message window the number for the values for the eigen frequencies, and we can also see in the results the total displacements, what will give us information about the modes. So this is mode 1. This is mode 2. This connected, linked to the roof. Mode 3, that is a mixed mode, mode 4, and mode 5. So with this, we see that mode 1 is actually the critical one, is the sway mode, so the one to be considered in the pushover. So we continue by setting up our pushover analysis. So here we have an analysis to which we add a structural nonlinear with 2 execute blocks. So first we consider the self-weight in 2 load steps, and we keep the equilibrium iteration properties as a default. And then in the second execute block, we impose the load, the pushover load into load steps. So this we want to load the structure until a failure. So we give a large number of steps. We also activate the arc length control. So in this case, this will have automatic steps of for the load, and it will help us reaching the failure. And because we are doing a nonlinear analysis until failure, we set some different properties than default for the iterative procedure. So we will increase the maximum number of iterations to 50, and we use the secant quasi-Newton method, and we select the convergence norm of displacements. So these are some extra settings for the nonlinear analysis. And for the output, so we ask for output in result steps of each 5 steps, and we ask for displacements, forces, strains, and stresses. And then we would run the analysis. I'm not going to run now because it takes a couple of minutes, and I will jump directly to the results of this analysis. So we already saw the mode shapes. So now we are going to see the total displacements for the increasing of the pushover load. So you can see the increment of displacements, and following that sway mode of the pushover, so the mode 1, so you can see the increasing of the displacements. And then in step 29 there's divergency, and Diana retrieves the immediately before step that has converged, even if it's not in the steps that are asked for output. So load step 28 would be the peak load, and load step 29 the divergency, the failure. So we can also see some crack widths for the localization of damage. So we can see some crack widths. So you can see the increment of damage with the increment of the load. And here would be the divergency. And now here the the damage at failure, and we can see here for the maximum of 5 layers. So we can see here in the localized in the door gap the maximum damage. To make the pushover load graph, so what we can do is to select nodes. So we can select a node of our structure, and we can ask for the displacements in X direction, so in our table, and we could copy paste this to Excel, and also select the reaction forces. So the reaction forces in a table, so not in that node, but in all the nodes. If we deselect the node, so we have the table, and here we could copy this to Excel and sum them all, and we would have the total base shear force, and then we can do our pushover curve, which is the total displacements in the X direction versus the base shear force, which is something I did here. So you can see this would be our pushover curve, and you see the last step before divergency. So we could also have doubts if this mode 1 was truly the dominant sway mode, the dominant mode for the pushover curve. So we could go back to our model and change our eigen mode to be considered in the pushover load. So we could go to loads and to the pushover definition of load, and change here the eigen mode to be considered to number 2. So eigen mode 2, if we see here in the displacements, eigen mode 2 is the one that is related with the walls in the to the roof, but we could also use mode 3, that is well, a mixed, or mode 4. So we select mode 2, and we could well, generate another well, this is for eigen mode 3, for example. So this would be, so for eigen mode 3, so for this mixed mode, so eigen mode 3. So we would need to remesh our model. We would need to run again the analysis and make the pushover curve, and we would have the pushover curve for eigen mode 3, and when we compare the two, we can confirm that our dominant mode is number 1. So it is more critical. It has a lower shear force capacity. So this is all, and thank you for watching. Before closing, just one remark is this model is also very well explained in one of our tutorials that you can find in our website, that is called Pushover Analysis of a Masonry House. So thank you and goodbye.